Let's give now an example of how all this stuff works. So we said that we can reconstruct a signal. So now here you see a kind of square wave, which is this one. Actually, the one that I'm drawing in black is the true square wave. The one in red is an approximation of it. Now we will see what does this means. Okay, so we have to consider the Fourier transform we have seen so far, and so we have to understand which are the so-called frequency components. So the trick is this one. So if we consider the phasors, as we have seen a while ago, phasors were two-dimensional vectors, so complex numbers in the real and imaginary plane, vectors that are rotating around the center with a certain angular frequency. And we know that those things corresponds also to our complex exponential function, the one that we used as basis in the Fourier transform. So this signal, the square wave, is quite simple because it's one of the ones for which you can compute quite easily, let's say, the Fourier transform by hand, so analytically. And then out of this calculation we can obtain the f of omegas, which in this case, because of these particular signals, are like this. So it comes that those frequencies are discrete, and the first term is called the fundamental harmonic, which is a sinusoidal term having a frequency corresponding to the longest period you can find in the signal. So here in this chart, the longest period is this one. So t equals 1 over f, and omega is 2 pi f, let's say t0, f0, omega 0. So the frequency corresponding of this phasor. So we said that the trick is to add all these phasors together, tip to tail. So here we have a vector like this. So this is the phasor corresponding to omega 0. Then let me zoom it a little bit in. Okay, so you see better. So this is the first phasor rotating like this with angular frequency omega 0. Then there will be another phasor. We have to add another phasor, many phasors. Actually, there is an infinite number of phasors that we have to add in order to exactly reconstruct our signal of interest. But we don't do this now. We just consider the summation of the first 1, 2, 3, 4 phasors. And so for this, we will not obtain the original signal, but an approximation of it. So this is what we mean by approximating a signal in terms of Fourier synthesis. It means to stop the summation at a certain point. So if we do this, then we have to consider that those phasors are rotating, but each with a different frequency. So this one will rotate with frequency omega 1, this one omega 2, this one omega 3. They all have a different initial angle, which is the initial phase. In this case, the calculation is quite simple because for this square wave, the initial phase is 0 for all frequency components. The length of the phasor is the magnitude of that frequency component. So we have to remember that the phasor is a complex number, so it comes with a magnitude and a phase. So here we see this in this picture. And then the summation means that we have to summate all of them. So let's see what happens to the trajectory of this red dot here as we make the time evolving. So let's see what happens. So you see, we get a 2D trajectory, a little bit strange, but it's the result of this summation of the phasors. Here you have a representation of them, so you see the one corresponding to the fundamental harmonic is rotating quite slow. This one is not present, this frequency is not present into this representation. It comes from the calculation of the Fourier transform. Then this one is smaller but faster, and also this one and this one. Those numbers here are the weights, so are the amplitudes here, here, and here. Okay, but then we have to remember that in the phasor representation, the signal was the real part of the phasors defined as a complex exponential, or the representation in the complex number. So we take the geometrical projection of this 2D trajectory onto the real axis. Now we arrange the real axis vertically, just for convenience of the plot. And then by this geometrical projection, we get the trajectory of this dot, which is representing in time our f of t. Okay, now we switch to a complete different topic. We try an impossible mission, which is try to explain quantum mechanics in one slide. So we don't need quantum mechanics in this course of electronics, and I'm quite confident that we can say that we don't need quantum mechanics at all in order to do electronics. This doesn't mean that quantum mechanics is not important in electronics. It is important, but it is important from the point of view of the design of the components, not for using them. So it's good anyway if we know a little bit of it, just to understand how different materials can be characterized, and what we need to know is to understand the difference between a conductor, an insulator, and a semiconductor. So quantum mechanics is more important for the semiconductors. Okay, let's try. The entire problem of quantum mechanics started about a century ago with some crucial experiments that were very difficult to explain according to what was the physics at that time. So particularly one of those problems was to try to understand the spectrum of emission or absorption of some materials like hydrogen. So if you take hydrogen and you energize it in different ways, it can emit different frequencies in terms of electromagnetic radiation, which basically means light. And you can imagine this, for instance, if you consider the hydrogen present in the sun, which is burning with, in very complicated way. But the result of this is that it sends some light. Then we can think of focusing this light into a prism. The prism splits the light into different frequencies. And if we project those different frequencies of light, which basically are different colors, let's say, on a screen, then we will realize one important fact, that those so-called spectral lines are not continuous, they are discrete. So you will see really some lines separated each other by a certain amount, which is even not constant. And that was the problem. How can we explain those spectral lines? So to try to make a long story short, people in the past they had an idea of what an atom could be. So they thought it was something like this: a nucleus and some electrons. So in the case of the hydrogen, it's simple because it's only one electron. And they thought in the very beginning that this thing could rotate around the nucleus in circular orbits, a sort of planetary model. So this thing had a number of problems because the most important of those problems is that if you consider this as a electron which is rotating, the laws of the electromagnetism says that when it changes direction, by changing direction means like this, so if it is the vector pointing the direction of rotation, by changing direction it should emit some radiation, and so it should lose energy, and so this trajectory will start decaying like this, like a spiral, and in the end the electron should fall on the nucleus. And basically this means that all the matter as we see should not exist, because if you compute this decay time is very very short, and this is obviously something which contradicts our experience. So this model can't be right. So they tried to solve it in different ways. At a certain point, some scientists had the idea, because of these problems of the frequency of the light, the spectral lines, they thought that there should be something wavy, let's say, contained in the behavior of the atoms. And at a certain point, somebody had the idea that this kind of wave should be something like this. Now I make a drawing that maybe in the beginning doesn't have a lot of sense, but now we will explain it. So they thought that there should be some kind of wave propagating somehow in an unknown, uncertain way around the atom, the nucleus of the atom. And because they had this idea of frequency connected to a rotation, they thought that this wave should be done in a way that the value at the beginning of this path should match the value of it at the end. And this you can understand it cannot happen for all orbits. It happens only for a certain set of radii. So if you make a smaller orbit like this, and you start drawing a wave, now I choose color, I change color with the same pattern, say like this, it is possible that when you arrive here, because you set the wavelength, so the distance between two peaks in this curvilinear path, so maybe this will not close. So for this, the radii are discrete, are quantized. Not all the radiuses are possible with this idea in mind. So how did they solve this problem? So first they had this idea to introduce this concept of periodical waves, closed loop waves somehow, in order to justify the presence of some discretization of the orbits, which then was useful in order to explain the discretization of the frequency spectra, which turned to be the frequency of those wavy things, and I didn't know what they were. Then secondary, if they consider the kinetic energy of the electrons, and now we have a representation of this kinetic energy here, and the potential energy, which is basically what makes the electron to be attracted by the nucleus, they defined an object which is called the Hamiltonian function. And if you study this Hamiltonian function, they were able to understand the behavior of these waves. One important ingredient that was missing and was found by scientists of the past, Schrödinger, was an equation for all this. So he found a very important equation which is called the Schrödinger equation, which makes use of this Hamiltonian object plus another object he introduced, which is this one, psi, the so-called wave function. Okay. So the Hamiltonian function, which somehow describes the total energy in the system, and this energy is discrete due to this periodicity argument here, and basically the kinetic energy. So these Hamiltonian functions plus the wave function describes what now we know to be called as orbitals. They had a good idea, but those functions were wrong. So if you consider the psi functions, they are three-dimensional, in this case of the study of the hydrogen atom. And if you plot the magnitude of those functions, they are like this. They define this kind of graphs that you see here in this chart. And we don't see this into details, but it is possible to associate the amplitude of these functions as the probability of finding an electron in a place around the nucleus. So here we have a color bar. So where the color is dark, the probability is very low. Where the color is bright, the probability of finding an electron is very high. So first you see that the electrons are not distributed evenly in all the space, but they have particular patterns. Those patterns correspond to those standing wave they were seeking for, and they are particular arrangement of electrons, and they are called the eigenstates. The real state of an electron is a combination of those eigenstates in a way which is similar to what we did so far with the Fourier transform. So you have a basis of function, and then with some weights you combine them and you obtain the function of interest. So for us this is very interesting, very important, but we don't do this now. We only need one piece of information. So the piece of information we need is that those wave functions are organized also by energy. So if I make those boxes, those boxes corresponds to specific values of energy E. All the eigenfunctions in a box, in a yellow box, have the same level of energy. This is the result of the study of the Schrödinger equation. Once the potential V, which depends on how the nucleus of the atom is done, so it depends on V and how V is defined. So once you give an atom, you have a specific V, you plug all these things in the Schrödinger equation, and then you calculate psi and the energies E corresponding to each psi. Okay, now let's move on. Let's now try to understand this chart we have here. So what we are representing here is the number of states. So let's say the number of wave functions in a certain way versus the energy of those wave functions. So here what we see is that when we consider the lowest possible number of states, the energy is already a little bit. So we are here in the graph. So it means that even in the most simple condition, an electron around a nucleus has got a little bit of energy. So then we can consider more energy, so we move up this way and we see how the number of states increases. So we go like this. So here we have a certain number of states, the density of states to be more precise. So if we increase the energy, we have a bigger number of states till a certain point. And then there is a turning point, so we continue to increase the energy, then we find that we reach this point in the graph. So if we are here, then we can again think of increasing the energy. We don't say how. Let's say that it's possible to give energy to an electron. Then, in order to observe other states, we need to overcome what is called the band gap. And then we arrive here. And then if we continue with this game, we have this behavior. Okay, what is interesting is to notice that the energies of an electron are divided into two bands. The blue one, which is called the valence band, so this one, and the red one, which is called the conduction band. And then another interesting thing is that we have a gap where we have no states. It means that the electron cannot stay having this level of energy. So the valence band is the type of behavior that the so-called valence electrons have, which are the ones that are very close to the nucleus and are responsible for binding one nucleus to another one, and so creating the chemical bindings, molecules. The ones that are in the conduction band up here have enough energy to be detached from their original nucleus and to travel around the material from one nucleus to another one. The materials that have a very big band gap are called insulators, which means that for those type of materials it's difficult to promote one electron to the conduction band. So they are poor conductors. Electrons don't move very well. They don't move, let's say, in an insulator. They might if I energize them a lot, so surpassing this gap. But in this case, what happens is that for the insulators, the electrons would have so much energy that they will create a lot of scattering, they will hit the ions of the atom, and probably they will modify, they will destroy the electron, the material. Basically, this is a so-called electric discharge in the material. Then the material changes, and then it's not very useful. And it's difficult to have this condition in an insulator, especially if it is a good insulator with a very high band gap. Then there is another class of material which is called conductors. So in the conductors, the two bands are overlapped, so the gap is not present, which means that it's very easy to promote an electron in the valence band to the conduction band, and also vice versa. So all the electrons are, let's say, interchangeable. And for metals, this means that those electrons are very easy to move. And we say that metals conducts electricity very well. So they are very good conductors. When we speak about metals in electronics, we will basically speak only about copper. Then there is a third class of materials, which are called the semiconductors. And the corresponding graph is similar to this one, but with a very small band gap. So a very small band gap means that the material is an insulator, but it's easy to make it a conductor. So you need to give energy to the electrons, but not that much, just a little bit. A little bit in order to have it here, but without so much energy that it will destroy the material. So those are very interesting because of this property. These are materials that can change their nature, so they can become a conductor or insulator depending on something that we can do on them, and they can also do this gradually. So it's a very interesting material, which is the basis of some components. So the first one is the diode, we will see this. Then another application, a variation of the diode, is the transistor. And then with the transistor we can do amplifiers, and with amplifiers we can do many things in both the so-called analog domain, and we will also see in the digital domain.